So, very quick review. We were dealing with radiation processes that are characterized through a perturbation that we wrote then V is equal to, and then we had a small v which was time independent, and then we had a factor e to the minus plus I omega t that carried the time dependence. And then we derived from this a rate, a transition rate, going from an initial state 0 to state n, and that was written as 2 pi over h bar times the matrix element of this time-independent part squared, and then we had a delta function that described the energy of the final state minus the energy of the initial state minus and plus h bar omega depending on the sign here. So this is how we had written it, and we had then interpreted this one here as a spectrum, and that tells us what's the probability that a certain energy is being absorbed, and we applied it then to transition, where we had the following kind of situation, where this one here was our energy difference that corresponds to this energy that we put in, or this sort of, we have an energy difference there, and so then we replace this one by a Gaussian that described actually that we had initially states here that were distributed. So we had initially a Boltzmann distribution P of Q, and so the initial state wasn't just one fixed state, but there was actually distribution of state, a thermal distribution of states that we accounted for, and then this one was then replaced by a Gaussian. So this is what we had. Now, in case that we have a non-radiative transition, then we just have omega equals 0. And we don't have radiation. And we still might have a perturbation, but we don't have a radiation, and we can still induce a process without adding from the outside energy. Okay, so now we went then on, and so this theory here described as the absorption and emission spectra of molecules, and so that was clearly one of those issues that we had to address if we want to understand photosynthesis. The process begins with light absorption, possibly being followed by emission, even though one wants to avoid it usually, but it might happen. And so that was basically the first quantum process in photosynthesis. And then we said that we have another process, and that is fluorescent resonant energy transfer. And that was a process where the absorbed excitation from the solar radiation was transmitted through the cellular system to reach the site where the energy would be converted into another form of energy, namely into charging a membrane. And this process, we said, comes about by having an energy donor and an energy acceptor. Donor, acceptor undergo a transition. Initially, the donor has its electrons filled, but one electron being empty and in an excited state. We call this one then phi d excited, and this one we call phi d the not excited. And then we have here the acceptor, which is initially in the state where all the electrons are energy-wise the lowest possibility. And here we have phi d, phi a excited, but is not occupied. And we have phi a being not excited, being occupied. And so then we have a transition then, where now the energy goes from the donor to the acceptor. And now we have the donor being in the lowest energy state, and the acceptor having now one electron promoted. And so here we are now in the state phi A excited, and here phi d excited is not populated, and so we have this transition. And now if we look, then we find that these electrons here are all unchanged. They are not really doing anything different from the left and the right side. They're exactly the same. And here the same here. So they're not changed, and so we can forget about them. This is an approximation, not exact, but it really gives us a principle very well. And so we only need to then look at the electrons that are really changing. And if you look here, then these are the electrons that are changing. And now we can say then that our initial state looks like it is a phi A state times a phi D excited state, and the final state is it's a phi D and the phi A excited state. So this is how the system looks like. And if we have now a perturbation, then the perturbation will be here, V will be equal to W times e to the 0, because there's no external radiation. We just have to live with the excitation we have, but there's not a radiation coming in that which adds or takes away energy, just this one. And then the rate that we have, that we are talking about, the rate for, maybe I write it now, d star A goes to d A star. So this would be d star A, and this would be d A star. That would be equal to 2 pi over h bar times w times final. So maybe I write it then d A star A w d star A squared times the delta function that just compares the initial and the final state. So E initial, also E final minus E initial. So that is what it would be. So this is, we called our spectrum, the probability that the energies match. So we need to have an energy criterion that is not just often a delta function, but can be a distribution. We call that one the spectrum then. And this is the rest of it. And then we calculated W last time. And we found that it is really due to the Coulomb interaction between D and A. And if we do this, then we are getting an expansion. And we did the expansion, I don't want to do it again. And then we found that the W, the interaction energy, the leading order is actually the following. It's already between D star A, D A star, the final one, doesn't matter which one we write on which side, and then D star A. So we found that this one was equal to, and then we had DD times DA times, so this one we just write the absolute values of those quantities. These are, that I will introduce them in a second, the transition dipole moments for these excitations in the donor and the acceptor. We have here an excitation, and we have here an excitation. So here we have an excitation. This is the excited state donor, and it comes with a transition dipole moment dd. And here we have an excited state acceptor, and it comes with a transition dipole moment dA. And here we just have the prefactor the absolute values of those transition dipole moments. And then we have here a quantity kappa that gives us the geometry. So this is sort of the quantum physics of the molecule, the transition dipole moments, and kappa is just a geometry, and kappa had the value actually kappa divided by r cubed. So there's an r dependence, and the r dependence is actually follows that if we have here our molecules again, D and A, then we have two centers for the molecules, and the centers we assume are described by a vector R that had the magnitude that I call capital R without the vector, and then of course it has also direction. And so this is a key quantity, and so this is the center of D, this is the center of A, and there's some vector that connects the two. And then we found that the kappa is the direction of the transition dipole moment in D, scalar product with the direction of the transition dipole moment of A. So these are unit vectors. So the magnitude is pulled out, and here we have just the unit vectors. -3 times direction of the transition dipole moment in D times the direction of this vector connecting the two R, and then the same. So this is just one scalar product, and then we have another scalar product, same for A. The direction of A, transition dipole moment, multiplies the direction of R. So this is how we do it. If we define for D and A, for those things, the angles, and then if I draw here for one of them, let's say this is D, I don't give it an index because it holds for either of them, and I go back into the plane of the y and x axis, then I have here an angle phi, and here I have an angle theta. Then this quantity kappa can be written as cosine theta, and I make this one here parallel to R. So I choose R in the z direction. Since I can choose any coordinate system I like, it shouldn't depend on the coordinate system, or there's something wrong with my formula, I can choose R to be the z-axis. And so then I get in cosine theta A times cosine theta D minus, plus or minus, I think it's plus, cosine, sine theta A sine theta D. Yeah, it depends now on what I define first and second. So I think it's cosine phi A minus phi D. And so this is this scalar product. I can write a scalar product like this. You might just look up your quantum book or your electromagnetism book, and you find that you can that this is the formula for the scalar product. And then this one here is of course just cosine theta D and cosine theta A. And so I'm getting now minus 2 cosine theta A D cosine theta A. And this one drops out, so you have a 3, but since I have here a 1, they cancel each other, I just get a 2. And so this is my final expression for that kappa. So you see how kappa depends on the orientational system. If we define R being the d direction, and then we can calculate it. And now if we put this into our formula, then we find that the transition rate for d star A goes to A d star is equal to 2 pi over h bar times this d star A w d, I don't know what it is, so I'm not going to repeat it. I just write now, this one is equal to kappa squared over r to the 6 times dd squared times dA squared, and times now a spectrum. And I give the spectrum in a second. And so this is what I'm getting. And now the spectrum is that I have to match the the emission spectrum of D with the absorption spectrum of A. And so if you have a molecule, any molecule, and I have here my emission or absorption spectra, and here I have E, then what you find is that there's a dividing line for drawing the spectrum, and one spectrum begins here and goes maybe like this, and other spectrum begins here and goes like this, and then this one would be the absorption spectrum, and this is the emission spectrum. And so this is just telling you that when you absorb, you have to put more energy in than when you emit. You always lose energy, because when you absorb a molecule, like here going from a ground state to the excited state, then when you go to the excited state up here, you go up here, but then you relax in the excited state to the equilibrium, so you lose thermal energy, you thermalize the system, and that is why one spectrum is lower than the other. There can be some thermal effect that you're getting a slight overlap. That can happen, but that's sort of small and more academic. So usually there's a pretty nice divide, and so that is how it is. And so if you want to use a donor, then the donor has to have a pretty high absorption spectrum in order that it can transfer its energy to A, because the emission spectrum counts. So this would be S absorption, and this would be S emission, and the poor donor can only work with its emission spectrum, which is redder than the absorption spectrum. So that is how things work. And so this is now what it is. Now you have integral. Yeah, okay, good, fine. So this is what you find. And so now you can do this for two chlorophylls, and that is what we did at the end last time, where we have now transition dipole moment for the chlorophylls for the relevant excitations. And so I'm not going to belabor that, which excitation it is and so on. We are already falling behind enough. So I just want to give you the final expression. And the final expression is roughly kappa squared over nanosecond times 100 angstrom over the separation of the two chlorophylls. So this is for two chlorophylls here. The separation between the chlorophyll, so chlorophyll center, separation between the magnesium ions of the chlorophyll to the 6th power. And kappa squared, looks complicated, what can it be, but you find it usually a quantity pretty close to 1. I mean, order of magnitude, and actually if you have a complete average, so when every angle possible contributes the same amount, because the molecules are freely rotating the chlorophylls, then it is 2/3. And so, but you don't really need to know. If you want to do precision tuning and get the absolute fastest rate, you use it, and you're getting higher value than 2/3. But in general, it's about 1, and if an average is 2/3, and not that much sweat about it. What's really crucial is this factor, And we know that if we're getting rate 1/nanosecond, that's not too good, because fluorescence is also 1/nanosecond. So we have to outpace fluorescence. And the only way to outpace fluorescence is this one needs to be much larger than 1 in order to have a rate that is much faster than the fluorescent rate. So 1/nanosecond is a fluorescence, so it's much larger than 1. That means you have to make this chlorophyll distance smaller. And if we choose it at 50 angstrom, then we're getting here 64. And 64 is a pretty good number. It's almost 100 times faster. That means that we have a good outcome. We're getting not quite 1% of the energy, 99% of the energy out of it, but sort of roughly 95% we would get if we have the 50 angstrom distance here. So we have to pack the chlorophyll very closely. So that was our result last time, and that's all interesting, but it turns out that if we do this 50 angstrom bit, that's not quite good, because it's still a little slow. We have to work a little more to make this excitation transfer faster. And what nature is doing is, so chlorophyll excitation transfer is slow. Now I'm talking now real big business. Like, let's say we go to human society. Human society, we are a little shallow society, but that's how normal modern society is. Everything that counts is money. So now let's say somebody gives you a trick how to get for each dollar $10. Like tells you invest there and you're getting $10 tomorrow. You would do that right away. That would be really important. It really improves your life. That counts. That currency for an organism is energy. Energy is of tremendous importance to biological organisms. So they really want to get as much energy out of photosynthesis as they possibly can. They don't want to lose it for fluorescence or other processes. So they really wanted to make the transfer fast. And so they thought hard about what to do. And so they did the following. They alter. Strategy is alter single chlorophyll excitation to excitonic excitation. Why this is good, you will have to figure out in your homework problem next time. This time you have to take my word for it. Next time you prove it yourself. This time you just have to take my word for it. I just tell you what is excitonic excitation. The next time you prove yourself, oh, that's a good thing to do. Okay, what's excitonic excitation? So you saw this in the pictures I show you, that that in photosynthesis the chlorophylls are forming in the bacterial system, in plant system and other bacteria. You find not quite the same, but in principle something similar. They form rings of chlorophylls. And so there were actually rings of chlorophylls, and in the case that I showed you, there were 18 chlorophylls forming a ring. And the way they do that is, if I now take it, I rotate it here by 90 degrees, then I'm getting the top view, and then I see that the chlorophyll Yeah, I draw it like this. It's not quite like this. I simplify. And I will tell you a little bit more about it. So we have here 2n chlorophylls, and 2n is equal 18 in the case I showed you, but we want to keep it sort of general. 2n. So this is what we have. So we have a ring of chlorophylls. And now you don't excite a single one, you spread the excitation around. And the way that works is as follows, that these chlorophylls are described by a Hamiltonian that gives us for each side an energy, which is the excitation energy of that particular chlorophyll. So epsilon 0 is single chlorophyll excitation energy. And then there is coupling between those chlorophylls, between those chlorophyll excitation. Where is this coupling coming from? Here, the W. This W is exactly the coupling. Except that you are not, except that this one here, these guys here, come from the W. Where you transfer the excitation from one chlorophyll to the next. So this one is a donor, this one is an acceptor. You don't have thermalization that comes from the spectrum. The spectrum tells you when you really excite one, it relaxes. Then you excite it, it relaxes. That way you lose a lot of energy. Here you are coherently exciting them. They're all getting excited at the same time. And they are not, you don't hop with the excitation literally from molecule to molecule and let it then vibrationally relax. Rather, you just spread the excitation coherently and forget about the vibrations for the molecule of the molecule for the moment. So just a W literally. Now when we calculated the W, we did a multipole expansion, and the multipole expansion only good when the molecules are further apart than their size. But these molecules are actually edge-edge, some of them are even overlapping. So for the close by, you cannot use the computational strategy we did, but Taylor multiple expansion is not deep physics. The multiple expansion is just, to do it in the classroom. If you're going to the computer, okay, I don't do multiple expansion because it's not allowed. I have to do it quote exactly, and you can do that exactly. You calculate it, and when you pull the molecules apart, your result will then finally agree after a certain separation distance with a multiple expansion. But when you get them closer together, you're getting a deviation. It's not like the deviation is a totally new world. You're making a factor, you correct, 1% error, 10% error, 20% error, 100% error, 150% error, but it's not like 1,000% error or 10,000% error, So basically it's the same W, except you cannot do when the molecules are too close, you are not allowed to do the Taylor expansion, the multiple expansion, otherwise the same. Okay, so then you're putting in here interactions, and since we're in the classroom, we are lazy, and we just put nearest neighbor interactions only, and say that beyond, for the moment, we don't want to include it. So now these molecules are actually completely symmetric. They have a real symmetry center. And so we have now a Hamiltonian where all these two ends are the same and the V's are everywhere the same. So we have really a Hamiltonian that is very symmetric. If C is a rotation by 360 degrees divided by 2n, and we rotate the Hamiltonian, we're getting the same Hamiltonian because everything is rotation is symmetric. So we have this rotation C, which is, okay, good, so the rotation C, that, now I'm using a little quantum physics nomenclature that commutes with the Hamiltonian. It means that when you transform the Hamiltonian, you're getting the same Hamiltonian. So it's famous, the transformation of a Hamiltonian through a symmetry transformation. It looks like this. This is a symmetrized Hamiltonian. This is a non-symmetrized, not moved Hamiltonian, but they're the same. So you have this one multiplied from the left side by C. You're getting here C, and this is the same as this one. So, okay. So if we have this kind of system, then we know that our states are eigenstates H n equal En n, and or maybe I call it psi n immediately, then it's a little easier to do the rest. And then I have C psi n is equal to lambda n psi n. So that vector is both an eigenstate of that symmetry operation as well as of the Hamiltonian. Now it turns out that this one we can find immediately, and then it turns out when we do it right, we are getting over the one there. How we find it? So we have that if we have a wave function psi that is in the state n and describes the j's, sorry, maybe I do it better like this. If I take the excitation of the j's phi j is so this one is the excitation. Maybe I write like sorry. Phi j is excitation of chlorophyll j. So we have my ring, and here I have chlorophyll 1, and here's chlorophyll 2n, and here's chlorophyll j. Then if that is the excitation of this chlorophyll, then C phi j gives me phi j plus 1. I move it one forward when I rotate. So I have this kind of behavior, and I know that C to the 2n phi j is equal to phi j again. If I rotate 2n times, then I'm back at the beginning getting phi j again. And this one here is connected with this one here. If you look here, I'm getting a little bit too elegant for a biophysics lecture, so I will stop here writing the result now. But anyway, so you see that this one is the same as this one. If I now do here C2n, then I'm getting here 2n, but the other one. So I know about my eigenvalues before I do anything. I know that ln to the 2n is equal 1. And so then I know how they look like, and they have to look like e to the in pi over 2n. If I have that one, then I go by 2n I'm getting 2n. If I do this, then I'm getting 2n. Then has to be a 2 here. Okay, down like this. Okay, so then it's correct. Okay, good. So that gives me a little bit of a guess. And now let me just write down the solution. And so the excitons have to be eigenfunctions of this symmetry operation that rotates things by an angle 2 pi divided by 2n. And you can convince yourself quickly that the psi n's have the following form. 1 over square root of 2n is just a normalization that you can, in this case, get very easily times the sum over j. Actually, I call it sum over alpha. And then we have e to the I n alpha pi over 2n times phi alpha. So this is how it looks like. And if you can very easily prove yourself now this is an eigenfunction of C. You can then also prove quickly it's an eigenfunction of H, and the eigenvalues are actually epsilon 0 plus 2v times cosine pi n over 2n. That's almost like what we did last time, except last time we had over 2n plus 1. This time we have over 2n because we have a circle and not a line, and so that changes the spectrum. Otherwise, very similar. Okay, so this is how the spectra looks like, and if I plot the spectrum, and here's E, and then I find I'm getting a lower state and a higher state, and then I'm getting many in-between states, and altogether I'm getting 2 n exciton states, and all the exciton states are double degenerate in the middle, except the top and bottom are not degenerate. So, but what else is degenerate? And so now if you have so the middle of this spectrum is epsilon 0, right in the middle, and if you have now chlorophyll excited, single excited, you have energy epsilon 0, and now it will assume one of those states when you put it, because it finds itself in a circle where it is connected with all the other chlorophylls, and the excitation will spread into all the other states. Now, since it's a thermal system, the excitation will spread that the lowest ones will be more occupied by the Boltzmann law than the highest one, so the lower one will be much more populated. So, and okay, good. And so that is how it is. And so if you don't have thermal process, you start with a single chlorophyll excited, you're getting a complicated wave function mixture of all this in time. But if you realize that it's really a thermal process where there's thermal damping, you're taking energy out of the system, and the real behavior is really that within a picosecond, you are getting the thermalized. The picosecond is not clear. That is sort of, you have to do some experiments to find it out. You get the thermalized excitons. So that is how it is. So you start with single chlorophyll absorbs the radiation, then zoom, it goes into all of the other excitons and makes the thermal population of all the excitonic states. And now the question is, why is this good? And I told you last time by telling you about the Girls' choir, that the chlorophylls are little They have little voices of little kindergarten girls and whisper to each other, and the voice doesn't reach far, so you cannot transfer the excitation very well to the other chlorophylls. Whereas the excitons are like a kindergarten girl choir. And when the girls sing for the kindergarten teacher, happy birthday to you, they really love the teacher and they are going to sing it, and you hear it outside on the street. Whereas if mama comes to kindergarten and the little girl sees mama, she says, mama, mama. Mama doesn't hear the girl, but she hears the choir when she approaches the building. So that is how you reach much further, and you can now transfer the excitation much faster through the system, and you don't lose it to emission, you don't lose it to thermalization. You can also take electron excitation, becomes also very often just vibration energy of a molecule, and that is being also not taking place, and that's why you go through the excitons. So for that way, we are getting the electrons, we are getting the electronic excitation energy absorbed by the molecules, and it's like a thermal absorption. We described it that we have then a Gaussian distributed spectrum rather than sharp lines, and then we are turning it into an exciton spectrum that is good for shouting the excitation all across the light harvesting system for photosynthesis, so that the excitation reaches within a few picoseconds to the centers, the so-called reaction centers, where now the energy is being used for electron transfer. So what we have is we have these small rings, and so single chlorophyll gets excited, and it turns it then into the excitation of an exciton. So it can happen, of course, in the same molecule, but so these are the LH2s, the protein that contain most of the chlorophylls, and then the exciton can go to this exciton. And then we had here now the figure 8 excitons with two reaction centers in the middle. And so now the excitation goes here to these excitons, and now it jumps to the reaction center. And in the reaction center, we have something that looks like this. This one is a membrane. And this is the inside of the chromatophore. And this is one is the outside of the chromatophore. But the inside of the cell. And so now we have here actually a pair of chlorophylls that get the excitation. So I have two chlorophylls, they form also an exciton system. Actually, there are actually really 4 chlorophylls in, maybe I make it 4, so there are 4 chlorophylls that form an exciton system in the reaction center. Now the reaction center takes the energy and transfers an electron to quinone. That's electron transfer. And so for electron transfer, likewise, via the W is a coupling. And so the electron transfer, the rate of electron transfer is then described just by our theory again. We have now here W squared times an energy conservation function. And that is how the electron transfer theory is described, except now we have an electron transferring, and here we have no radiation. It's thermal. So omega is equal to 0, but otherwise it's just the same theory, just a theory of excitation transfer. Here we transfer an electron. here we have W goes goes 1 over r to the 6. Here this W goes as e to the minus r over r0. So it is an exponential decay because the electron tunnels, and there's a tunnel through areas where there's not enough energy, and so this is how the electron goes. Now the electron really goes in steps. There's one step here, there's a second step here, and then third step here. So it's sort of like sub-steps, but so it doesn't go in one tunneling motion, but rather in 3 steps. But otherwise, this is how it is, and so you have now basically the same kind of theory, except the quantum mechanical entity that is being described here is an electron and not an exciton, but otherwise you also transfer it. The coupling goes not like, so W goes like 1 over r to the cubed, W squared goes like 1 over r to the 6. Here we go e to the minus r over 0, and then of course e to the minus 2r over 0 gives us the rate and how it depends on the distance. Okay, so you saw that there's really a lot of quantum physics going on in photosynthesis, and that I wanted to describe to you. And so now I just would like to summarize it, and then we go to our next quantum process, which is vision. So now let me begin here. Okay, great. Okay, so maybe we turn down the light a little, and so here we have our chromatophore, and here we have now a close-up view, and here we see the 3 proteins that contain the LH2, that they each contain rings of 18 chlorophylls. And so the chlorophylls absorb light individually, but then they share it quickly in an exciton mode, and within a picosecond it's thermalized in the excitons. And now they can go from one LH2 to another LH2 to a third LH2. And then they jump to the red one, where we have an exciton that now forms this figure 8. Still an exciton. You can have all kinds of shapes, and the quantum physics doesn't care if it's a ring really. In the classroom you like it a ring, but in quantum physics it doesn't really matter. And then you jump from this exciton to the reaction center, which is shown here in red and here in blue. And this is where you utilize the energy for electron transfer from inside to the outside. And so that's how it is. And you see that the proteins, this is really the packing of the proteins in the real system. It's not just a cartoon, but rather the real thing. And you see that the packing is rather close. So you know, you cannot pack it closer. So you really have to use quantum physics, namely the exciton coupling, to transfer the excitation. The next time you are calculating in a homework set, in principle, in a simplified model, how this transfer goes, and that when you are in an exciton state, you're actually getting faster transfer than when you just do it for the individual chlorophylls. Okay, so here we have these processes that we have to describe, that we had summarized last time of our last slide. Light absorption, we described it. exciton formation, we described it. Excitation energy transfer, we described it. Electron transfer, we described it. And these ones we don't cover, are a little bit more complicated, more chemistry, so I don't want to bother with it. But you see that very nicely reminder that what we actually have done has really something to do with biology. This is really where physics and life meet, and life forms in billions of years played around with the physics and exploited it to their benefit and to outdo the competition, and that was the driving force, and they did very well. So this is the photosynthesis, and now I want to start a totally new chapter, although it's still dealing with quantum biology, so some of it is actually not so new for us. It will remind us of what we did already, but we also learn a few new things. And so we begin with the beautiful science of vision. So for vision, here we see a color vision and Van Gogh painting, and we will also pay a little bit attention to color vision. How does it work that we can see colors? And it looks like maybe not so surprising, but you will see it's actually surprising, because the color vision that you use here in your eye uses the same molecule. It's not like we have one molecule for blue, one molecule for red, and one molecule for green, but rather we have only one molecule. And even though we only have one molecule, we can see the different spectra. And so that's where nature apparently used a strategy that the physicists might not have tried. And so we learn about it. So how is the eye looking like? So that's what we know. But this is how it looks like when you go to medical school. So we have here the length of the eye, and we have here the protective cornea that just protects it, but here is a lens that can really be accommodated, can be thicker and thinner, and thereby change the focal point. If you have to look at something closer, it becomes thicker. Look something further away, it becomes thinner. Then the light goes pretty much through this whole eye here. What in the middle is actually largely irrelevant from a physics point of view, but then at the end the light hits what is called the retina, and the retina is where the light receptors are located that detect photons and tell the brain about it. They tell the brain where a photon has been detected. So here you see the receptors in yellow, and you see then also in yellow the nerve cells that go to the brain, and so this is how it all works. Okay, so let's have a little closer look, and here we have an eye. You might ask, how can I do this? Whom did I kill to get that eye? It had somebody had to be killed, but you cannot get me to court for it. You can go in Illinois to the slaughterhouse and ask for cow eyes. And they give you a cow eyes. It's actually one of the most beautiful experiments you can do for yourself, to dissect a cow eye. And the most interesting part of the cow eye is actually the lens. So you cut in the cornea, you make an incision, and then you can get the lens out. You have to be very careful, because the lens is amazing. It looks like glass, totally transparent. You put your finger, it's like a magnifying glass, absolutely amazing. But then you squeeze it a little bit too much, and then it disrupts very, very easily, and it's totally milky, and you can't look through it anymore. So it's maintained in a state pretty robustly that you have a crystal clear view through it. But then when you push it a little bit too much, then you are getting it opaque. The reason is very simple. The system avoids like hell to have any structures that scatter light. Light is being scattered by anything that is about the wavelength of light. The wavelength of light is 400 to 800 nanometer. So you avoid any structure that is 400 to 800 nanometer, then it's clear. But when you are disrupting it, or for example you have water, and it has smaller structures, but it doesn't have structures 400, 800 nanometer, and you put milk in it, you're getting molecules that have about the size of 400 to 800 nanometer, and the light gets scattered and you cannot look through it anymore. And so same happens here when you disrupt it, that it's, and how nature makes it is really absolutely amazing story. It's an amazing story. I could give you just a whole lecture on it, what nature is doing, how it's doing this one. It's just, the main problem is that the energy transforming part of the cell, or which we talked about, we have something similar in human cells, have exactly the size of 400 to 800 nanometer. They break, they diffract the light, they scatter the light, and so you cannot have any energy transforming stuff in there. You have to have it outside of this whole lens, even though the cell is made of many cells. But these cells don't produce energy. The only thing they take is the molecules that are energy rich. And so this is an amazing system of cells that have a very easy passage of molecules diffusing from cell to cell. So it's really very interesting and great. What kind of molecules are these energy-rich molecules? How do they pass from cell to cell? And so this is one big sort of cell almost, because molecules can go from each of the cells to everyone to avoid that energy is manufactured there and then light is being scattered. But anyway, okay. So here's the eye, and now the eye is actually protected to the outside by some kind of leathery substance, often called also the tapetum, and the leathery substance that protects it against vibrations and possible injury and so on is actually also really like tapestry. That's where the word comes from. It's a Latin for tapestry, because for many animals this is actually reflective, so that they can see at night better. Here you see the what is it? I should know this, but I know it only in a raccoon. So you see the raccoon, and the raccoon actually uses the light photons twice at night. When they come in, they have one chance to absorb them. When they didn't absorb them, they're reflected by the tapestry of the eye, go out, and have a second chance to see them. That way they can see better at night. And so all the animals that want to see better at night, their eyes glow in the dark. And so you know that, of course, from cats, a little bit dogs, cows even. But some animals do it more than others because they really have to see better at night. So it's sort of one of those little physics things that you see. Okay, so this is that one. But now we look a little bit more closely to the retina, and this is actually this film here in front of the tapestry that is exposed to light. And we see here cells that are light sensitive. And now you would think, oh, light must come from here. No, light comes from here. Here we have the cells that are actually already part of the brain. The eye is actually an outer part of the brain. When you see it in embryonic development, then you see there's a brain, no eyes, and then suddenly something developed from the brain and exposes the nerve cells of the brain to the outside and makes those nerve cells light sensitive. And that's the reason why light comes actually from the top. There's no way that nature could find out how to expose the brain without having light come actually from this side rather than from the bottom. In primitive organisms, you have light come from here, where you can do more tricks and they don't have a real brain and so on. But we have a brain and we cannot do it. So we have it, the light comes through here. Now this one is here an incredibly well designed part of the brain. What you are doing is here a lot of computing to get information out of absorption of light. One of the most important things I always tell my graduate students, they make the mistake all the time. They have nothing to do with biology. Every physicist, now you listen to me. One of the most important things is that the color receptors. So you have here cells, as you will see, that are color receptors. These are actually the ones that are here in gray, where the red ones are just for night vision. And the one in gray, they are for color. And now when you look at this, how they read off the color, then you find that they do that by getting the input of the color receptors over a certain area. And so what I tell my students always, when they make color images or they make lines in color receptors are area receptors. What do? They sit that close to the computer, they make a very thin line, they can see it's red, but when you are going a little further away, or you put it on a not so great printer, or you put it here, you don't see the color anymore. Because you are having then now, it looks very thin, you just get 1 or 2 receptors, and this machinery here cannot read the color anymore. They need to average over a certain area before they assign a color. So, okay, but there are many other interesting things. For example, in lower animals, like frogs, when they want to catch a fly, they cannot say, oh, I think, what is a fly, brain? What should I do about it, brain? Oh, you better catch the fly. How do I do this? Oh, put your tongue out. Okay, let me do it. Here, I sent you a message to the tongue. And then the fly will be gone. What this system is doing is, when it thinks it has a fly, so it's sort of not too big of a spot, but a small spot going across, that this sends right away to the tongue and a signal to get that tongue out. So within a millisecond, there is a signal coming to the tongue. In birds, pretty high animals actually, they have to make such rapid motions when they fly that much of this output, what they see goes what is called the limbic system to orient the bird properly, that they know where's up and down and left and right and so on, goes straight out here. Whereas in us humans, we send everything first to the brain, and then the brain tells us what to do with the visual information. So we have a much less intelligent machinery here than frogs and birds, but better resolved so that we can do more things with the data that comes. So we are big data people. We send big data to the brain, and the brain is then doing some amazing things with information, whereas frogs and birds, they are not big data, but they are quick data people, animals. They do things fast. So really, there's a lot of things going on here, very, very interesting, and I could go on and on, but you know, we want to stay with the quantum biology rather than with the neurobiology. Okay, so there we have the receptors, and now how many receptors do we have here? We have here more receptor cells. Here you see the cells. We have more receptor cells than the United States has citizens. So a huge amount of receptor cells, very well resolved. So really, like, our camera is pretty good compared to those pixels that you get in your iPhone, and so it's not shabby. Okay, so now the nerve cells have to leave the eye, and they do that all at one spot here. If this is the eye, there is a symmetry axis to the eye. Good, it goes here. It doesn't go there, that would be bad. It goes here, because here, literally, where they go out, we cannot see anything. That's called the blind spot. So if you look at it here, then you take a cow eye. You can prepare this one out, and then you have the retina hanging like a skin hanging down, and all hangs on this nerve bundle, many nerve cells, the ganglion nerves. You hold them here, and where they enter here is a blind spot. Okay, so we do an experiment. Can we turn on the light? So now, so you distribute that quickly. So many of you might have seen already the blind spot, but it's sort of interesting to see it. So even though little Mickey Mouse, we want to look at it. And so now here we have it. You have to hold it like about this way, and sort of if you go like very stretched out or very close, and it works pretty well. I tried it just a few minutes before class. Okay, now what you do is you close your right eye, and you look with your left eye here, and then you move this, and you try to pay attention to this spot, and you see that at one certain distance the spot disappears. When you go with your arm longer, it comes back, and when you come closer, it also comes back. But there's one point where it is gone, and that's exactly the blind spot. And so it's so you can play it, you can impress your friends with it, whatever. And so, okay, good. So this is okay. So now we have in the, maybe we turn off the light again. We have in the eye, we have now several receptor cells. First we have totally. I think we need to go. Okay, so we have on one side we have what are called the rod cells. They are very long, and then we have the cone cells. They are more pyramidical and shorter, and the cone cells are for color vision, and the rod cells are for night vision. When we don't have so much light, that's of course extremely crucial. So we spend a lot of real estate on night vision, but more in the periphery, in the center of our eye, called the fovea, we have more cones. Here you see different cones in green, in blue, and here in red, those are the rods, and they are more on the periphery. In the center, we have the cones and many more cones. So they are unevenly distributed, and we have actually 3 cones for 3 different colors, and we have one rod that absorbs yet at another wavelength, and so we have actually in our eyes, cells that are maximally sensitive at 4 different wavelengths for the eye, for the light. And all using the same molecule to achieve that. So here you see the distribution. I told you already that in the periphery we have more one, and in the fovea more the other. Okay, so now the eye is a photon receptor, and the way it works is with the molecule retinal, and I showed this to you already. Retinal is initially in this form, and the molecule doesn't like to be in this form, but it is brought to this form through enzymes outside of the eye. They rotate the molecule that much more prefers to be straight into this form, and then puts it back into the eye. And now you see here's a carbon with 3 hydrogens. When you count your hydrogen bonds well, you'll find out there must be 3 hydrogens here. Here's one carbon with a hydrogen. They don't like each other here. They fight like dog and cat. And but you know, they're caught there. But when light comes, they can go straight. And they really like to go straight, and it happened then very, very rapidly. So a frustrated retinal, that's the name of the molecule, becomes an unfrustrated retinal. And that is the photo process that takes place there. So we have the retina, then the rod cells in the retina, and the rhodopsines that are the proteins that contain actually the retinal. And here you see the rod cell, the cone cell, and here you see the rhodopsine. It's a protein, a membrane protein that sits in a membrane. Here is sort of like a membrane, and it has what are called alpha helices. And here you see the retinal inside there, surrounded by groups that are charged or polar. And the reason why the retinal can absorb different wavelengths is that it's surrounded by molecular side groups of the protein that shifts the spectrum. So the retinal is a good absorber, but it has another nice property that its spectrum can be shifted easily through the environment, and quite dramatically from not quite from the blue 400 nanometer, but more sort of like from 500 nanometer all the way, not the 800 nanometer, but the 700 nanometer. And so you can really shift it around, and so nature said, there we got something, good absorber and a good spectral shifter, so we can do the whole job with a single molecule. We don't need to have, you know, synthesize 4 molecules for the eye, but rather only one. And we just make the proteins a little different. And we have, you know, in the human body, 30,000 proteins. What the heck, make another one and change the environment a little bit. So that is how that works. And now you see here the photoreaction. So here you see, at the moment when light absorbs, you see how this moves around here. And when you look at the molecule, then you find that this carbon here is what you call trans on the other side. When you go along here, right side, this carbon left side, this carbon right side, this carbon left side, this carbon right side, left side, right side, right side. This was initially, if I go back, this was initially on the other side. So now you see it was on the other side, and now it moved over. There it moved over. That's the whole thing that happens. But the molecule is now cramped. It's not happy. It's even more frustrated at this moment than it was before light absorption. And now the molecule will now really re-stretch out. Basically, you got your arm twisted, and now you untwist it and you stretch against the protein, and thereby you make the protein a new protein, a sensitive protein that is active, and tells the brain, I tell you in a second how that works a little bit, and tells the brain, a photon has been absorbed. So you're just making a very local change that translates in an overall geometric change of this retinal molecule. So the molecule is first like this, then it goes like this, what is unhappy, and then it goes like this, now I'm happy. But in stretching out inside the protein has to give way, and thereby you make a protein that is inactive in the protein that is active, and shouts to the brain, I absorbed a photon, I absorbed a photon, and that is what you want to achieve. Okay, here you see the energy. We go from to the excited state in red, This is a ground state, so we go here, we are in the excited state, and then the states cross, and we are now the ground state becomes the excited state, and the excited state becomes the ground, and we are going down. So that is the key point that happens in this molecule. You go from you are sitting here, you are going to the excited electronic state, but you just don't stay there. This is an unhappy molecule, I remind you, and so the molecule moves now away. Finally, it is out of the prison cell. It moved away. Now it comes to the point where actually excited and ground state cross, and now you are going to a new territory, but in the ground state. Now the molecule is in the ground state, very stable. Here, any moment you could do emission. Not very good, but here good because you're in the ground state. No emission possible. There's no lower state anymore, and so now you transform the molecule to a new molecule, and you see it happen very quickly, 80 femtoseconds. And so very fast process. And this is actually a variant. This is not really the molecule in the eye. The molecule in the eye is actually faster than this. This one is, just had only this available for you guys. I apologize. In the eye is about 10 times faster than this. So the eye goes zoom, and here it is like a little bit like a random process before it goes, even though 80 femtoseconds is fast, but compared to what's in the eye, this is random. So in the eye goes really fast. And so even faster than what you see there. Okay, so this is actually the protein in the eye. It's called rhodopsin. You see here the membrane, and you see here the eye. You see here the rods and cones, and here you see inside of these guys, there are all these. They look like pancakes, but the pancakes are inside hollow. So the pancakes they are made of a membrane. That is the top membrane. The bottom membrane looks like one round pancake. Inside hollow, and inside of this membrane that around the hollow pancake is where these molecules sit, and where you are changing their form. You see, initially the retina is curved, and then it becomes straight, and it alters the molecule. It alters the molecule actually not so much here, but rather on this surface. The surface now becomes an active surface, a signaling surface that tells other proteins what to do with themselves, and thereby generates a signal. So this is really the rhodopsin that you see in the eye. But the other protein is very similar, so it's not like I told you wrong. So this is a reaction, I told you already. And now how does it work? So I showed this left side is just the same, and you become to a point here where we cross to the ground state. I showed this to you. And so here we come down here, now we cross to the ground state and go on. And this is actually the physics of it. Because it's very important that here it looks like you have no other way, but it's not so easy. So it's possible that you go like jim, and then you go out of this little local hole, but you want to go down here. You come from here, you excite, you fall down here. Now you want to continue here. You don't want to go here because then you were where you were before. You want to go here, and you also don't want to go here. So you want to go from here to here, and that's what you need to control. And that all is a process that just takes a few femtoseconds. So it's real physics. No chemistry whatsoever, they're just real physics, and that is what we need to understand if we want to understand vision. And you call this one is a potential surface, and this one is a potential surface. It's a ground state potential surface, it's the excited state potential surface. You want to cross from one to the other, and you call that potential energy crossing, and that's really the key of the visual process. So visual process, you need to absorb light, you need to be able to shift the spectrum around, and you have to be very efficient in crossing the potential surface and in the right direction. Go there and not here. So that is the physics. So now, how do you do the signaling? So I told you that the retinal sits here in these discs, or pancakes, or we want to call them. And now the way it works is that you have just like in a, oh, we are way too late, sorry, oops. I apologize, I didn't pay attention and you were very kind and didn't remind me. We continue the next time. Okay, thank you very much.